Good morning, everybody. We have a guest speaker from Virginia Tech, Dr. Jason Legrow, today talking to us about post-quantum cryptography with advanced functionalities. Thank you very much, Jason, for coming.
Thank you, thank you. Yeah, it's a pleasure to be here. I've been wanting to come down for a while. I know we have a lot of good cryptography people here. It's also, I know, two minor issues. It's right after spring break, so everyone's a little exhausted. And also, as I was saying before we started, we just entered summertime, so the clocks went ahead. So everyone's a little, I think, a little exhausted for that reason as well. So hopefully I'll go a little slow maybe, and we'll have an easy time. But there's plenty of time for questions, I think. So please stop me if you need to ask anything. Also, I just wanted to say, I'm going to be talking mostly about blind signatures. I'm going to mention other advanced functionalities in the middle, but mostly this is about blind signatures. My work on blind signatures, so there's sort of one paper and one manuscript. So the first is with the paper with Shuichi Katsumata, Yifu Lai, and Wing Chin from various places. This was at Crypto last year. And then other work with Veronica Gupta and Eduardo Persichetti, who Veronica's here, but I'm sad that Eduardo can't be here, but I'll see him later this week, I hope, if he's back. Anyway, so I just wanted to shout out my collaborators. So, of course, this talk is mostly for crypto people, but still, I feel like it's important to sort of begin at the beginning in case there's anybody who really, who wants to to learn from the beginning, who hasn't seen a lot of this stuff before. So I want to talk about one of the most fundamental concepts in cryptography, which is key establishment, and in particular, I'll talk about Diffie-Hellman key establishment. I mean, if you take a public key crypto class, this is probably the first public key cryptographic protocol you would see. So what's the goal? The goal is for Alice and Bob to have a public conversation and leave with a shared secret. So they're sitting maybe in a coffee shop or something. They're talking back and forth. Everybody can hear everything they're saying, but still we hope that at the end of the day they can have a shared secret. What do I mean by a shared secret? Well, it's two words, right? Shared and secret. Shared means they should have the same piece of information at the end, and secret means that nobody else should have that piece of information. So that's our goal here. So Diffie and Hellman proposed, well, what we should do is take a group G, which is generated, a cyclic group generated by this thing, little g, of prime order P, and do the following. So I'll explain what's going on here in these slides. So what we've got is Alice is going to choose a secret integer x between 0 and p minus 1. She'll construct her piece of public information, capital X, which is g to the power little x. She sends that over to Bob. Bob does all the analogous things, except everything he has is called Y, little y and big Y. He sends Y over to Alice, big Y. And now Alice, using Bob's public information, big Y, and her own secret information, little x, she can construct this thing, which I call Ka, as Y to the power little x. Bob, of course, can do the analogous thing, construct X to the power little y. And then, again, what we hope is that at the end of the day, they have a shared secret. So we hope they have the same piece of information and that nobody else has this piece of information. So the shared part is captured by this notion of correctness. So what we observe is that y to the x and x to the y, well, these are the same, because they're g to the power of little x times y. So indeed, they have the same thing. Of course.
Who's Bob?
This is Bob Ross. He's a famous painter. Yeah. He was from The Joy of Painting. He was always talking about the happy little trees. Yeah, I guess these people are more familiar to Americans. I'm not American myself, but I still recognize it. But if you're not from the US, you might not recognize these people. Oh, he's on German too. See, okay, great. So it's not just here. Excellent question. Right. Yeah, so Alice and Bob, they've agreed on this. They have this shared thing. As for the secret part, well, that's captured by the security notion. And sort of at its most, if you boil it down to exactly what I care about in terms of security, it's that it should be difficult to find the secret thing, g to the power x times y, given the two public things, g to the power little x and g to the power little y. Finding that is called the computational Diffie-Hellman problem. And this problem is a little too on the nose, I think, for security purposes. It's literally saying, can you break the scheme or not? But normally we want to boil these things down to sort of a more natural, maybe, computational problem. And I would argue that the following computational problem is more natural. So given g to the x, find just x. This is called the discrete logarithm problem. And this is what the security of everything, like lots and lots of classical cryptography is based on. The idea of given g to the x, find x, and that being difficult is where your security comes from. And from a classical perspective, we've had a lot of time to think about this. And the group that you use makes a huge difference to the security level of the protocol. And what I mean by this is that the difficulty of solving the discrete logarithm problem in a group G depends heavily on what the group G is. In particular, if you take G to be the additive group mod P, then in fact, this is trivial. Veronica's teaching number theory this semester. You probably taught them the Euclidean algorithm, right? That's how you, so the Euclidean algorithm, or maybe the extended Euclidean algorithm, will solve the discrete logarithm problem in the additive group mod P. So this is trivial. It takes time polylog P, so this is easy. If you look instead inside the multiplicative group of a finite field, discrete log takes time some mess. So e to the something, and then in the exponent, this is something that's like smaller than log P, but not constant. So this is sub-exponentially hard. So this is what I would call a medium hard problem, maybe, in the literature. You don't want to have sub-exponential attacks on your protocols, but even if you do, that doesn't mean they're insecure necessarily. But then if you look at the as a subgroup of an ordinary elliptic curve, well, then you're doing really well. The best algorithms for discrete logarithm problem take time p to the theta of 1. So basically, they're as bad as exhaustive key search, which is as bad as you can get. I mean, that I'm hiding a lot in the exponent. The exponent is actually like a third or a half, not 1. But still, it's asymptotically sort of behaving in a similar way. So the group that you choose for Diffie-Hellman for the discrete logarithm problem makes a big difference to how hard it is. And I say this from a classical perspective. And what do I mean by this? Well, you all probably know because you've got your quantum or post-quantum cryptography research group here. And so this is in contrast with the quantum perspective. And in the quantum perspective, this group that you use in Diffie-Hellman makes pretty much no difference to security, as I'm sure we all know. The reason is that we can write down a very compact quantum circuit. And I mean, even if you don't know much about quantum circuits, which I don't, I think when I made this slide the first time, I knew a lot more than I do now. I've forgotten most of it. But the idea is that this is a very compact circuit. Everything that I can draw a circle around with my cursor is easy to implement. So the h to the n, that's trivial. This is like baked in. This is like one of the most fundamental things. Quantum Fourier transform, that's easy enough. Measurements, those are easy. And then this is just operations in the group. These are all, you don't need to worry about what they are exactly, but the point is that these are things that if you have anything that if you can like legally call it a quantum computer, you can do all these things. Otherwise, you wouldn't be able to call it a quantum computer. And so to find little x such that, so define the value of the discrete logarithm, you just need to implement these gates that I've labeled here, and then this arithmetic in the group basically on a quantum computer. So that will break your discrete logarithm problem, and that will mean that your Diffie-Hellman based thing is insecure. So it's great. It seems like we had a solution to a problem of having a shared secret that you can use, say, for an asymmetric algorithm, or sorry, for a symmetric algorithm. There you go. But now it's completely broken by quantum computers. And so the takeaway from this is that what we're going to need are primitives which are not known to be vulnerable to quantum attacks. I mean, ideally, we want them to not be vulnerable to quantum attacks, for sure. That's a difficult thing to prove. If you can prove that your classical crypto system is immune to quantum attacks, then like you've proven a separation between BQP and NP or something, which is pretty difficult. You know, if like the best complexity theorists in the world have been thinking about this for a long time and haven't made a lot of progress. So we're going to need things that we don't know, we believe to be invulnerable to quantum attacks. And those things are called post-quantum protocols. So there's sort of 5 main research directions. People here, I'm sure, are familiar with all of these. So there's lattice-based. This is probably the biggest one. A lot of lattice-based protocols. Multivariate polynomial-based. I don't know if anybody here has worked on that. The last time I gave this talk, there were multivariate people. Oh, there are multivariate people here. Very cool. Oh, I'm glad. Hash-based stuff. These are quite interesting. Oftentimes, these have sort of like a limited number of uses. Although it's a very large number of uses, you can sort of bootstrap it. It's a very, I don't know. Hash-based stuff is very cool, although I don't do it myself. Code-based cryptography based on using error-correcting codes sort of not for their intended purpose, which is kind of cool. Like they're used normally to give you some sort of data integrity, but you can actually flip them around and use them for a hardness assumption. And then, so when I started working on this stuff, the 5th category was called other. But I think we've decided now what other means is super singular isogeny based, which at least I'm declaring it so. I mean, I've said this many times. Many people have seen this slide. Nobody's complained yet. We're pretty sure that other is just, I mean, so actually maybe now there could be a 6th category, which is honestly called other, because there are people looking at non-abelian groups for cryptography, other algebraic systems. I don't know a lot about those yet. I'm hoping to learn more eventually. But for the purposes of this talk, I'm most interested in code-based and supersingular isogeny-based. Why is that? Well, I've been interested in isogeny-based cryptography since I started my graduate work. This is what I did in grad school almost exclusively, or maybe entirely exclusively. But I've become interested as well in code-based stuff because right now, these are the sort of two frameworks, sort of the two areas that use the group action framework, which is a very versatile framework for analyzing and constructing cryptographic protocol. A lot of my recent work has been wondering, like, okay, if I can make something in isogeny world, can I translate it to code world by considering group actions? And it turns out that it's not so trivial. At least it doesn't seem to be. Anyway, but this is what I like to work on right now. So that's what I'll be talking about in the rest of the talk mostly. I guess this is all pretty basic background stuff, but it's a fine time if you have questions. No, people seem okay. Yes.
Is this code stuff vulnerable to empty like computers? Or not like deterministic brain machines?
No, I don't believe so. This stuff should be as secure as the classical stuff, at least. Yeah. So I wouldn't expect it to be to have any attacks from classical computers.
I said non-deterministic brain machines.
Yes, non-deterministic Turing machines are. I mean, you mean algorithms that can solve any NP problem, for instance? Is that what you're?
Yeah.
Okay. If you can solve any NP problem, then I think we're in really bad shape. Yeah, then probably everything is broken. Sorry, I misunderstood. Yeah. If you can solve any NP problem, yeah, this is all ruined. Cryptography sort of has to be based on NP problems, because you need to be able to verify that you have the right answer at a certain point. Sorry, I'm not a complexity theorist, but that's fine.
I mean, maybe you could have verify that it's a setup, but it's all add uncertainty.
That's an interesting idea, actually. I hadn't considered it that way. Yeah, this is outside my wheelhouse for sure. We should talk later. Yeah, if you look at if you want to see if anybody has worked on this, look at the TCC Theory of Cryptography conference. That's where you do the most esoteric kind of cryptography. So I imagine that's where you might see something about that. All right. Okay. So maybe before I get into advanced functionalities, in particular blind signatures, which is what I'm going to care about for the rest of the talk, I should talk about basic public key functionalities so that I can sort of contrast them. And like I said, I talked about key establishment before. When I think of public key cryptography, I sort of think of three main public key functionalities that you've all probably used today. You probably haven't used blind signatures today, but you've probably used all three of these things. So I showed you a key establishment protocol. This is used to establish a shared secret. These are used, of course, for symmetric key primitives. Crypto systems, so encryption, decryption, these are used to ensure confidentiality, possibly among other things. And then we have also this notion of signature scheme, which are used sort of in the same way that you would use an ordinary, like a signature, like pen on paper signature, where we ensure that message integrity, so messages haven't been tampered with. Data origin authentication, where we're sort of sure about who produced the message and who sent us the message. And then non-repudiation is sort of protects, it sort of goes the other way around, where if you produce a signature, a third party can then convince a judge that you really produced the signature. So you can't renege on the contracts that you sign. So these are sort of the fundamental public key cryptographic functionalities. I imagine if you took a public key crypto class here or anywhere else in the world, you would have seen these three things. And I imagine you guys teach it, so you've taught all this stuff before. And this is enough for many applications like web browsing or Zoom or whatever, things that we use all the time, every day. But more and more services are moving online and or electronic. I mean, a lot of things want to be online, but even just doing things electronically, locally, sometimes will require some kind of additional functionalities. And unfortunately, the security guarantees and the capabilities that you get from key establishment, encryption, and signatures, these are not enough for everything that you might want to do. So for instance, what might you want to do that these things are not good enough for? Electronic voting is a big one. So electronic voting, you don't want people to be able to, read your vote. So there's a secrecy aspect, but there's also an authenticity aspect because whoever is like counting your vote needs to ensure that you were eligible to vote in the first place, right? So there's sort of competing ideas there. And then also you may want this to be like a transparent or auditable process. That's also something that is not easily captured by the notions from before. A huge thing right now, of course, is computing on encrypted data. If you have maybe a huge data set or even a small data set that you want to perform huge computations on, you're probably going to want to outsource that to a cloud computing service. But if your data is sensitive, then you don't want to send it in the clear, right? Even if you send it encrypted, if you want to work on it while it's encrypted, that's not so easy. Like if you encrypt something using I don't know, Elgamal, or RSA, computing on it is not very easy. So that's something we would need an advanced functionality for. Sort of continuing in that vein, what if maybe your data is sensitive, or maybe it's even not, but what if the algorithm you want to run is sensitive and you want to outsource this to the cloud? So evaluation of sensitive algorithms, this is something else that these standard cryptographic primitives are not sufficient for. And then some things that are a little bit simpler to understand, but still we would like to do them more efficiently, like joint account management. So if 10 people share authority over a bank account, do you want to have to produce 10 signatures every time you want to do anything? Probably not. Can we do this more efficiently? Or can we delegate the authority in a non-trivial way? Can we say these collections of people, these subsets of people are allowed to construct signatures, these subsets are not, and then do this in a straightforward, in an efficient way. Authoritative leaking, this is something that I found very interesting, where suppose you're working on the board of directors of some big company who's doing something sort of shady, and you want to leak that information to the press in such a way that they're going to believe that you would know this stuff, but your identity is not revealed, so you can't be retaliated against. That's the idea of authoritative leaking. So you declare yourself as a member of a class, say board members, but you do not reveal which board member you are. This can be done using ring signatures, for instance. Anonymous payments, so being able to purchase things anonymously online. Maybe your first thought when you hear this is probably to be doing unscrupulous things, but also supposing you live in a place where the politics are sort of authoritarian, and you want to be making donations to a rival political party, to the ruling one, right? This is something you would want to do anonymously. So there are sort of above board uses for this as well. These are all things that cannot be easily done using the primitives that I talked about on the previous slide. So we need to introduce new protocols with advanced functionalities. And then not only that, we also need them to be post-quantum, right? Because if the quantum computers come and break all this stuff in the classical way, then we're out of luck once again. So there's sort of two parallel tracks that people are trying to work on in cryptography. There's post-quantum and there's advanced functionalities. And I work sort of on both together. I want advanced functionalities and a post-quantum. Yeah, there you go. So we're going to need new protocols to support these advanced functionalities, and we're going to want them to be post-quantum. I'm going to be talking about blind signatures, of course. So what I'll do first is talk about what a signature scheme is. This I'll try and go over quickly because I'm sure we all already know more or less what a signature scheme is. Like I said, intuitively, it should be have the same security properties as putting your real signature on a piece of paper. So it's 3 algorithms. The first algorithm produces, this is not the interesting algorithm, it produces a signing key and a verification key. The idea is you keep your signing key to yourself. You don't tell other people how to make your signature, but you show other people your signature. So they need a way to verify that it's yours. So that's what the verification key is for. You share that around. There's a signing algorithm, which takes a message and outputs a signature. It requires a secret key in order to do this. And then there's a verification algorithm that takes a corresponding public key, a message, and then a signature, which hopefully was generated with the signing algorithm using the secret key. And then it outputs a bit, which says it's either valid or invalid. So it's just, the signing algorithm for an ink on paper signature is I take the pen and I produce my signature on the paper. And the verification algorithm is you look at it and you look at all the other signatures that I've ever produced and you say, it looks the same. So this is probably right. But of course, in the digital world, things are a little different. As it turns out, we basically don't need to study signature schemes, even though we want them, because there's a transformation that turns what's known as a zero-knowledge proof into a signature scheme. And these zero-knowledge proofs are much easier, at least to me, to study than signature schemes. And the transformation is called the Piaget-Shamir transform. So we can transform zero-knowledge proofs into signatures. So what we're going to do is we're going to study zero-knowledge proofs. And indeed, we're not even going to study zero-knowledge proofs in full generality. The last time I talked about this stuff, I mentioned, so Sigma protocols, they're basically good enough for everything. But it turns out actually in the code-based setting, sometimes you want a 5-round protocol. And someone there was like big on the 5-round protocol. But here, nobody wants the 5-round protocol. We want the simplest possible thing. This is a Sigma protocol. So what is a Sigma protocol? It is a 3-round protocol, highly structured. And the idea is that Alice is going to convince Bob that she knows this thing, SK. This SK is linked mathematically through some computational problem to the public key. And Bob knows the public key. So maybe what you want to think about is in the setting of the discrete logarithm problem. This is sort of the canonical example. So suppose Bob sees g to the power of little x. Alice wants to convince Bob that she knows the value of little x. That's what a Sigma protocol will enable her to do. She's going to prove that she knows the exponent corresponding to the public key that Bob sees. So how does it go? Well, they all sort of work the same way. These Sigma protocols are really structured. Alice is going to choose some randomness according to a distribution. She's going to construct something called the commitment. She'll send that over to Bob. Bob, now he'll see the commitment, and he will choose something called the challenge, send the challenge over to Alice, and then Alice will use her randomness, her secret key, her commitment, and her challenge to construct what's called the response. And then there's some function that checks whether the commitment, challenge, and response are valid or not. Valid means that Alice really knows the secret key, and invalid means Bob is not convinced that Alice knows the secret key. So there's some function. And of course, I haven't put any details of what this thing would actually look like in practice up here. So you might say, well, does this make any sense at all? Can you construct these? What would it look like? But this is just the generic structure. We can talk now about a particular example. But before I do that, I'm going to talk about the security of these things. So again, in cryptography, we always have a security notion that goes along with every protocol. So for a Sigma protocol, we need correctness, which says that if everyone is honest, if everyone does what they're supposed to, then the proof will go through. Everything will look the way that it should. Bob will agree that Alice knows the secret key. Soundness protects Bob against cheating Alice. So if Alice doesn't know the secret key, Bob should reject the proof with high probability. And by high probability, I actually don't mean that high. If he rejects it, as long as he rejects it with constant probability, we're okay. So probability 1/2 or probability 1% even, that's fine. That's all we need. Higher the better, of course. And then the other way around, we want to protect honest Alice against curious Bob. So this honest verifier zero knowledge property says that if Bob behaves the way that he's supposed to, he still doesn't learn anything about the secret key. So that's where the zero knowledge property of the name zero knowledge protocol comes from. Bob doesn't learn anything about the secret. Okay, so here's an example. This is the canonical example from the literature, the Schnorr zero knowledge proof. It's for exactly this thing that I said before, this discrete logarithm relation. So Alice will have a secret key. Her public key is g to the power of the secret key. Bob will see the public key. He wants to be convinced that Alice knows the secret key. So what are we going to do? Alice will choose r uniformly at random between 0 and p-1. She'll construct the commitment as g to the power of r. And in the classical world, at least, this doesn't really reveal anything about r to Bob because he can't compute r using just a classical computer. Bob's challenge will also be a number between 0 and p-1. And then what Alice will do is she'll construct her response as r plus the challenge times the secret key, mod p. And then Bob is going to compute everything in the exponent. So g to the power of the response, that's going to be g to the power of r plus the challenge times the secret key. And he's going to check that that's equal to the commitment times the public key to the power of the challenge. So this, I mean, there's a lot of sans serif text here, so it's maybe hard to parse what's going on. But if we look closely at what's going on, so the commitment, that's g to the power of little r. There's going to be an r up here, like it's like g to the r in this exponent here. And then public key to the power of the challenge, well, that's going to give me secret key times challenge. And so I'm going to get r plus secret key times challenge up here, and that's also what I've got on the left here. So this protocol, at the very least, I should convince you, is correct in the sense that it makes sense if you work out the math. The other security properties, well, hopefully this is not a proof. Let me just preface this by saying this is not a proof, something I say to my students all the time when I'm just giving them some intuition. We see that the response, constructing the response, at least using the formula that I've given you, requires Alice to know the secret key. So hopefully we believe that the secret key is required to actually construct the response. There's a formal proof of this, of course. So this thing should be sound. And then the honest verifier zero knowledge part, well, the response is the only thing that depends on the secret key at all, and it's masked by a uniformly random value. So Bob should learn nothing about the secret. So this protocol, as it turns out, is secure. Is that all right? Oh. So great. So this thing works fine. In fact, it's basically the best possible Sigma protocol because like one of the main things that makes a Sigma protocol efficient is having a big challenge space. And this is a gigantic challenge space. So that's great. This is like the best Sigma protocol you could ever want. But it turns out that when we move to the post-quantum setting, when we want to use group actions, we're going to run into a lot of trouble. So why is that? We'll see why in a second. So in Schnorr, the commitment and the public key are group elements. So Bob can compute the pk to the power of the challenge, because we're just in a group, and then you can multiply by the commitment, because again, we're still in a group. Great, we can do all these group operations. Of course, as I discussed, we saw the quantum algorithm. In the post-quantum setting, Schnorr can never be secure because no matter which group you take, you can solve the discrete logarithm problem on your quantum computer. So instead, what we're going to do is to try and get quantum security. We still want to work in a group, but we're going to consider instead a group action. So if you've taken like your second abstract algebra class or something, you've probably seen a bunch about group actions. So what is a group action? Well, it's nothing more than a way of thinking of a group as a collection of permutations on a set. So these are, you've got your abstract group. It can be a cyclic group. It can be, a dihedral group, whatever kind of group you want. But then you think of each element of the group as being a function from a set X to itself, permutation of a set X. And this has to play nice with the group operations. What do I mean by that? So if I want to think about, so maybe I'll walk up, sorry everyone, you can't see what I'm doing, but walk up to the projector screen. So this dot here, I'm saying I'm going to act H on X. So I'm going to compute the image of X under the function H. And then if I do that again, but with G, this should be the same as first multiplying G and H in the group. And then that's a new function and acting it on X. So that's all a group action is. It's a way of thinking. Of course, you pick the right set X. Otherwise, it's not very useful or interesting. So in group action-based cryptography, you're still going to want your secret key and your public key. Your secret key is going to be a group element, kind of how it was before. But your public key now is not going to live in the group anymore. It's going to live in the set X. And what are you going to do? Well, you're going to take your secret key SK. You're going to act it on some fixed X naught. That's now going to live in the set X. So you pick a distinguished X naught. How you do this depends on the setting that you're in. In isogeny-based crypto, it's super easy. You're always picking the same X naught, basically. In code-based, I actually don't know what you do. Maybe you pick one randomly or something. Doesn't really matter. But the point is that the public key no longer lives in the group. That's really the big takeaway here. The public key no longer lives in the group. It lives in the set X. So there's some hope of post-quantum this year, as long as recovering G from G acting on X naught is hard, because that's exactly the problem here, right? I got the secret key. The public key is the secret key acting on some fixed thing. So as long as it's hard to recover SK from PK, there's some hope of post-quantum. But a Schnorr-like protocol is totally hopeless. And I put an asterisk here because, what do I mean by Schnorr-like? I haven't really explained. But the point is, I cannot compute the public key to the power of an integer because the public key doesn't live in a group. And I can't multiply it by the commitment because public key does not live in a group. So we're gonna have trouble. Okay. But it turns out you can still make zero knowledge proofs of knowledge in the group action setting. And hopefully this is relatively comprehensible. So my Alice, again, she's got her secret key. She's got her public key as I described it. So you take the secret key, you act it on some fixed thing. Bob has the public key. He wants to be convinced that Alice knows the secret key. So what's going to happen? Alice will sample a group element from the group. Her commitment will come from acting that group element on X naught. She'll send that over to Bob. Bob will take a challenge. The challenges now are 0 or 1. So just only 2 possibilities, much smaller. That's a lot worse. He'll send that over to Alice. And then Alice's response will be G if the challenge is 0, or G times the inverse of the secret key if the challenge is 1. And then we can check that these equations will hold. So if the challenge is 0, she's going to check that the commitment is the response times X0, or acting on X0, which of course it is because the response is G, and that's literally the definition of the commitment. The more interesting case is when the challenge is 1. When the challenge is 1, this is going to be G times the inverse of SK. So what's going to happen when when Bob acts the response on PK is that this SK inverse will kill this SK here, and I'll be left with X naught, and then I'll be multiplying by G, so I get my commitment again. So this protocol, this works, and I haven't used any properties of the group here. This is great. This works for any group action. Well, okay, it's correct for any group action. We don't know, it's not necessarily secure. All right. So which group actions do we care about in cryptography? Like I said, there's sort of 2. There's these code-based ones and these isogeny-based ones. So I'll explain very briefly what these are. So the code-based actions that, here we go, that I have been interested in are, first one, complex multiplication on supersingular elliptic curves. I'll explain what that means in a second. Let me just, there we go. And then the other one is this notion of code equivalence. So acting on codes. They've got some pros and cons. So for complex multiplication, the group which acts is cyclic. It's the ideal class group of the number field. Well, okay, it's not always cyclic, but it's cyclic for our purposes. So lots of stuff looks exactly like Diffie-Hellman. In fact, you get a key exchange protocol that looks exactly like Diffie-Hellman, except everywhere you would have a group element, you just acted on a multiple curve. The big problem with complex multiplication on supersingular elliptic curves is that in this talk, I don't even have time to tell you what the group or the set are. And that's not a problem with this talk. That's the length of the talk. That's a problem with the complicated math that lives underneath all of this. So there's like a huge learning curve for learning about this stuff. So that's kind of unfortunate. Code equivalence is basically exactly the opposite. So the groups and the sets are super easy to describe. The groups that are acting are groups of matrices, general linear group. So just groups of invertible matrices. Everybody, even if you don't know a lot about those groups, you've at least seen them before when you took linear algebra. And then the things they act on are vector spaces. So something, again, when you took linear algebra, you learned about them. But the problem is matrix groups aren't abelian, usually. The ones that are boring. So this is really difficult, makes some things very difficult. So in particular, you cannot get key exchange in a straightforward way. If you could make code-based key exchange from group actions, that would be a pretty important paper, I think. Anyway. So that's sort of the two. These are basically opposites of one another. In one of them, the math is hard, but the group is nice. And the other one, the math is easy, but the group is bad. Or maybe it's good. We'll see. Okay. So moving on quickly, I want to talk about exotic signatures because I want to talk about blind signatures. That's sort of the big thing for this talk. So exotic signatures are variants of signature schemes which provide different or enhanced functionalities. And I'll just list a few, just so you know that there's, because I'm going to talk about blind signatures, but there's more than just blind signatures. There's a whole class of protocols. So here are some that we've been able to get out of group action. So threshold signatures, these are signature schemes where you've got a bunch of people, signing authority is delegated among a bunch of people, and enough of them have to cooperate in order to produce signatures. So it's sort of like a delegated management of a single account. Ring signatures and linkable ring signatures, these allow you to sign on behalf of a group of people without revealing which group member you are. So this is used for authoritative leaking. So for instance, you sign on behalf of the whole board of directors, but you don't reveal which member you are. Adapter signatures, these are confusing. What they're used for is atomic swaps. Basically, they allow two mutually untrusting parties to exchange goods without the use of an escrow service. We can talk about it later if you really care. I think they're extremely cool, but they're just hard to explain in a sentence. And then blind signatures. These are used in an interactive way in order to get signatures on message which the signer doesn't see. And that sounds insane, right? Why would you sign something? If I came to you with a totally redacted contract and asked you to sign it, would you sign it? Of course you wouldn't. But it turns out these are useful for some things. And that's what I'm going to talk about now, are these blind signatures. So generically, this is what a blind signature looks like. I expect you to learn very little from this diagram, but there's one really important thing at the end. So Alice has a secret key and a public key, a signing key and a verification key. Bob only knows the public key, and he has a message that he wants signed using Alice's secret key. They're going to do some local computations and exchange some messages, some number of rounds of messages. And at the end of the day, the important thing is that Bob gets the signature on the message. Bob learns the signature on the message. Alice learns nothing. So Bob comes to Alice and says, I want you to sign something. She says, great, let's do it. They talk. At the end of the day, Bob gets the signature and Alice doesn't even know what she signed, nor does she even know the signature. She learns really nothing. So it sounds, yeah, it's like, why on earth would you ever want this? But this is, it turns out, a very important class of protocol. And in particular, just in contrast with everything else I've listed on this slide, blind signatures are interactive. So that makes them very difficult to analyze in practice. So there was a big paper at, I think, AsiaCrypt maybe 2 years ago, where they proved that like a bunch of blind signatures, the proofs were all wrong, and the new proof is like 60 pages long anyway. It's a very hard thing to read. Veronica had to deal with this one on the paper that we were working on. Anyway, but the point is they're a very complicated object with a very good, which are very useful. Maybe I'll explain. I don't think I have a slide explaining why they're useful. These can be used for electronic voting. The idea is that the signer here will be an elections official. She works for, okay, when I gave this talk the first time, I was in Canada, so she works in Elections Canada. I can respond. I will respond to your question after the talk. Maybe it's not 60 pages. Don't quote me on that, but it's long. Anyway, so yeah, when I gave this talk the first time, I was in Canada. I live there. I vote in Canada, so I'll talk about Canada. There's an Elections Canada official who has the signing key, and then I'm there. I want to vote in the election. The Elections Canada official will look at the roll and see, yes, Jason Legrow, he lives in Kitchener Center. That's where I lived. He is allowed to vote in this election. Great. And then she and I will engage in the signing process where my message is going to be my vote. So at the end of the day, I'm going to get my vote endorsed by the Elections Canada official, and she will not read my message. She will not know who I voted for. And then I can put, my signed vote in the box or whatever. So that's what these blind signatures, that's one of the things they're really good for. The other thing is for anonymous payments. I won't talk about that because I'm going much slower than I anticipated. Okay, two main security notions. We've got this notion of one more on forgeability. What it says is that if you see T signatures, you can only produce T signatures. You can't make T plus one or more signatures. So this sort of makes sense because you're allowed to ask for signatures in the security game, but you need to not be able to produce more than you've asked for. So this protects honest Bob against cheating, honest Alice against cheating Bob. But there's also a blindness notion where honest Bob must be protected against cheating Alice. Bob must not be able to, Alice must not be able to tell which message signature pairs correspond to which sessions. Phrased differently, Alice must not be able to know which messages Bob has asked for signatures on. So that's the blindness idea. The blindness proof, if you look at the papers, it's always less than a page long, pretty easy. It's just some straightforward probability stuff. And as I said, one forgeability, significantly more complicated. It's a very difficult. I don't really understand all the details of the proof myself. There's this new framework that anyway. Kastner, Loss, and Zhu. If that got transcribed correctly, you can look for those names. Those are the authors. Okay, so here is the Schnorr blind signature / zero knowledge proof. It's sort of both at the same time, so it's interactive, so it looks like a zero knowledge proof. Much of this is the same as before. They're still choosing the randomness. The commitment is constructed as it was before, and the response is actually exactly the same as it was before. So actually, everything that Alice is doing is the same as what she was doing before. The difference is that Bob is doing much more work. Well, because it's a different kind of protocol. So Bob has this message he wants signed. And what he's going to do is he's going to choose these alpha and beta, which I'm going to call the blinding parameters, which he's going to take this transcript, commitment, challenge, and response, this is what we call a transcript, and he's going to blind every part of it. He's going to mask them by adding or multiplying in the group. So for instance, he's going to construct the blind commitment by multiplying by this thing g to the alpha times public key to the beta. He's going to construct the challenge. This comes from the Piaget-Shamir transform by hashing the blinded commitment with the message. And then he's going to construct the challenge, the honest challenge that he sends to Alice. He's going to construct that by adding beta onto chal prime, the blind challenge. He's going to send it over to Alice. Alice will construct her response as usual. And then Bob, well, first thing he's going to do, we look here, he checks that Alice knows the secret key. He's going to check that Alice is acting the way that she's supposed to. If not, he's going to say, well, this Alice is lying to me, I'll give up. Otherwise, now he's tasked with producing a signature, right? That's the idea. At the end of the blind signature protocol, Bob needs a signature on his message. And it turns out this blind commitment and this blind response are sufficient to make, and along with, you can throw the challenge in, or sorry, the blind challenge in as well if you want. Turns out you don't need to. And that will be the signature. The signature is like the blind is the transcript blinded by Bob's blinding parameters. That's basically the idea. So this looks, if you're familiar with Piaget-Shamir, which many of you are, this looks a little bit like Piaget-Shamir. That's where the challenge is coming from. But there's also a blinding component. So there's sort of two modifications. Yes. Oh, I'm sorry. That must be a typo. This S is supposed to be the response. Oh. The original response. Excellent point. Sorry. Maybe I was a little sleep deprived when these slides came together. So yeah, S here is the response. So he takes the response and adds alpha. I think it's corrected on the next slide. So I just wanted to point out in orange here, hopefully this comes through, where the blinding aspect is coming in. So Bob is blinding the commitment. That's the first thing with the orange. He's blinding the challenge, and he's blinding the response. So all three things are sort of obfuscated by Bob. Okay, so for Piaget-Shamir like blind signatures, we had to blind all the aspects of the transcript so that the signature cannot be linked to the signing sessions. Because what Alice sees is the transcript, the things going back and forth in the middle here. But what the signature is obtained from the transcript by adding and multiplying. So it will look different. It's like a one-time pad kind of thing. So what we saw was that the chal prime was chal minus beta, res prime was res plus alpha, and com prime was com times a bunch of stuff. And you should immediately see, well, okay, maybe that's not true, but you might see where this is going to go wrong in the group action setting. But what I want to emphasize is that your choice of how you mask your challenge and response determines how you need to mask the commitment, because there's some like underlying equation that needs to be satisfied at the end of the day. And in particular, if you look at the Schnorr blind signature, if I mask the challenge by subtracting beta and the response by adding alpha, then in order to mask the commitment, I need to multiply the commitment by g to the alpha and then again by x to the beta. This works great in the Schnorr setting, of course, but when I move to group actions, it's completely hopeless because the commitment isn't a group element. And this x here, that'll be the public key, also not a group element. So I can't raise it to the power of beta and I can't multiply it by anything. So totally hopeless in the group action setting.
So here, do you need alpha beta to be uniform?
Yes, in order for the proof to go through, yeah, you want this to be chosen uniformly at random. Okay. Here's a zero-knowledge proof for a cyclic group action. This is what's used in Seaside, as it turns out. I've already talked about a group action base. I'm not going to talk a lot about this, but I just wanted to put it up there again because I'm going to talk about it on the next slide. The blinding aspects at least. So here's a zero-knowledge proof for a cyclic group action. We've seen this before on an earlier slide. Just wanted to refresh your memory. And so this cyclic group action zero-knowledge proof, this is the standard one used in isogeny-based cryptography, is not super amenable to blinding. The reason is that if I go back, if I want to blind my commitment, that's what Bob should be doing over here. You got to blind the commitment. The only thing it seems like you can do is act another group element on it, right? So he chooses an exponent and computes g to the y, his new exponent, acting on the commitment. So suppose that's what he does. So he gets his blind commitment is g to the r plus y acting on x naught. In terms of the challenge, well, there's only two challenges, right? So Bob's only choice is to keep the challenge the same or flip the challenge. And this must be done uniformly at random in order for blindness to hold. Alice will give Bob the response. Okay, I'm going to, just for instance, I'll suppose that the original challenge is 0 and the blind challenge is 1, because otherwise there's too many cases for me to analyze one by one, but this is one of the ones that fails. So this is easy. So in this case, if the original challenge is 0, the response is R. So Bob now knows R, but he needs to respond to chal prime equals 1. So what does he need to do in order for that? I won't, I mean, if you sat down and worked it out, I'm sure you could figure out what it needs to be. But because the blind challenge is 1, Bob needs the blind response to be R plus Y minus the secret key. He knows R and he knows Y, doesn't know what the secret key is. Bob has no mechanism to construct this. So the natural thing you would do to blind this protocol simply does not work. Bob cannot construct the correct response, the correct blind response, because he doesn't know the secret key. So we need some way for Bob to be able to rig up the right response without knowing the secret. It turns out that in Seaside, so what is Seaside? Commutative supersingular isogeny Diffie-Hellman. So supersingular isogeny in there. This is an isogeny-based protocol. It turns out that the group action used in Seaside, which I haven't even defined, doesn't matter, it's cyclic is what matters, is actually more expressive than an abstract group action. How is it more expressive? So the commitments and the public keys will look like this. There'll be g to the power of z acting on x naught for some secret key little z, right? That's what the commitments and the public keys look like in the protocol that I showed you. It turns out what we can do is construct g to the power of minus z acting on x naught, where what I'm able to do is negate the exponent. It turns out this computation is easy. It's super easy in the Seaside setting. And this is really interesting because actually in the Diffie-Hellman setting, the analogous thing is really hard. So we actually get some more functionality in the Seaside setting than existed in the Diffie-Hellman setting, which I think is really cool. If you go back, there's a password authenticated key establishment protocol based on the hardness of computing the analogous thing in the Diffie-Hellman setting, but it's easy in the Seaside setting. Anyway, what is it? If you care about elliptic curves, the point is our elliptic curves are going to have some equation y squared is equal to x cubed plus ax squared plus x. If you want the inverse of that, like negative z in the exponent, you just simply negate the quadratic coefficient. Doesn't matter. If you know a lot about elliptic curves, this will be clear. If you don't, it won't. This thing is called the quadratic twist, and it turns out that it's pivotal to the blinding in Seaside. So here's the new protocol that we're able to blind easily. Hopefully I can get through all of this in the next few minutes. So this is the same protocol as before, actually, the same cyclic group action protocol from before. But the difference now is that the challenge is not 0 or 1, but it's -1 or 1. And what we're going to do when we, so the response is still the same, R minus the secret key times the challenge. And what you're going to compute at the end, the interesting thing about this is that it always involves the public key. It never just involves this x naught from before. If you think back, so when the challenge was 0, What I wanted down here was for was X naught, not the public key. But now the challenge can never be 0. I only want to consider pk to the 1, so that's just pk, or pk minus 1, the quadratic twist. And if you sit down and you compute all the exponents that appear here, you'll see that this is a correct protocol. So there's this slight change. I've changed the challenge space, and the corresponding checking algorithm now uses the public key either honestly or its twist. So Bob now, when he wants to, so remember, he has the commitment, Tom, from Alice. He wants to blind it. What I said before was the only thing he can do is act on it by g to the y for some randomly chosen y. But now, with this new power of the twist, he can also choose whether or not to twist the commitment. And that will correspond to a bit 1 or minus 1. So if it's 1, he doesn't twist. If it's minus 1, he does twist. So now his blind commitment will be g to the power of y acting on not just the commitment, but the commitment which potentially is twisted. And he's going to set the new blind challenge to be d times the old challenge. So now what happens? So the case that I had before was that the blind challenge was 1, the challenge was 0, Bob was hopeless. Now what happens if the blind challenge is different from the challenge? So the blind challenge is minus 1 and the challenge is 1. This corresponds to the setting of d equals minus 1. So Alice, if we go back to the protocol, will give the response, sometimes I call it S, is R minus the secret key, the randomness minus the secret key. Bob needs to be able to respond to the other challenge, chal equals minus 1. But let's see what that means. If chal equals if the blind challenge is minus 1, Bob needs to construct a response, blind response, which satisfies g to the power of the blind response times the twist of the public key. Remember, the challenge goes up into this exponent here, and he wants that to be equal to the blind commitment. The blind commitment should be, oh, sorry, there's a missing R up here somewhere. But the point is, if I had written this line correctly, what we'd find is that the response has to be y, or the blind response must be y minus the original response. And this is something that Bob can construct. So I'm sure if I correct a typo on the slide and then we sit down and we work out the mathematical details in the exponent, everything will work the way that it's supposed to. So this, by changing the sigma protocol, it becomes more amenable to blinding, and that allows us to construct a blind signature. Bob knows why. I guess that's the important thing. Bob chose why up here. Great. Okay. So at 10:50, I'm sure, especially the day after spring break, I don't want to, take up too much time, but I'll just very quickly talk about what happens in the code setting. Many of you are code experts more than I am, so maybe this won't be too confusing. So for my purposes, a code is the row span of a matrix G. So you take your matrix G, you multiply on the left by every possible vector. That gives you a vector subspace of some vector of this, f to the fp to the something. The group, this matrix group, this pair of matrices, acts on the set of codes by right multiplication by the tensor product of the transposes. Doesn't matter, just think of it as vector multiplication. And really what's happening, the best way to think of this is that if I act AB on the code X, I change the generator matrix by multiplying on the right by A transpose tensor B transpose. This is the easiest way, I think, to think about this group action. It's used to construct matrix equivalence digital signatures, MEDS, invented at this very university, or at least by one of the people at this university. You want to use it for blind signatures, but there's no analog of the quadratic twist. Also, the group is not abelian, so that's really bad. But even worse, there's no quadratic twist. So what can you do? So our goal now is to adapt the blind signature construction to this setting. In the seaside setting, I was able to compute the quadratic twist by twisting. Easy to do. It turns out that in the code setting, you could just give everyone all the twists they would need. Suppose at some point they would need the twist of something. You could just give them it at every step. So every commitment, every public key will include the twist analog from before. And what do I mean by the twist analog? So if the public key is AB acting on X naught, then the twisted public key, I'm going to denote it as A to the minus 1, B to the minus 1 acting on X naught. But what is A to the minus 1 in brackets, B to the minus 1 in brackets? It's actually the inverse transpose. And this is quite non-trivial. Your intuition says maybe it should just be the inverse, right? Because that's what it was in the seaside setting. But it turns out what you need, what's special about the transpose is that it's an involution which plays nicely with, it's an order reversing involution which plays nicely with the inverse. So what happens now is This operator, the minus transpose, the inverse transpose, is an order preserving involution, which turns out to be exactly what you need to make a blind signature. I don't have a lot of detail. So in the protocol, there's going to be some blinding. There's a twisting here, a blinding by a randomly chosen thing, and then the challenge and response are blinded in a similar way. In order to verify, we're going to need to satisfy this. This is like the fundamental equation, of blind signatures. The blind commitment must be equal to the response acting on the public key to the power of the blind challenge. And then if you check the details, sorry, this looks like a big mess. What you'll see is that what you need to have happen, if you refer just over to the far left of each side of the equation, I've got yr to the d, zs to the d acting on x naught on the left. I want that to be equal to the thing on the right. I've still got yr to the d, zs to the d acting on something else acting on x naught. What I need is for this to be the identity, because the identity acting on x naught will preserve x naught. So this whole thing will become x naught, and then the two sides will be equal. It turns out, in order to make this equal, I just need to be able to take A and B be symmetric. So that turned out, this eluded us for a long time. But the secret to making these blind signatures out of codes is to take the secret keys to be symmetric or anti-symmetric. It turns out it works just as well. But that's a technical detail. Anyway, so we'll end on some future work / open questions. What else? What other classical techniques can we adapt to the abelian group action setting? So the C-side setting, basically. This is something I really didn't touch on, but the group that's used in C-side is called the ideal class group of a certain number field. Turns out computing the structure of these things is really hard, and you need it. You need the structure of these things in order to do everything the way that I explained it. What can you do with the group if the structure is unknown? Some of you may have seen the protocol C-sign, SEA-SIGN. That is one of the few works that works when the structure is unknown. What about in the code-based setting? Is there a quadratic twist analog? Like, can what I said on the previous slide is that I'll just give you the twist. Every time you need the twist, just ask me for it and I'll give it to you. But is there a way to not do that? That would reduce the communication load by a factor of 2, which is pretty cool. Or some alternative constructions that don't need the twist. The group is non-abelian. Can that enable us to get new constructions that abelian groups can't do? That would be cool. Also, the group action is non-transitive. That might also be useful. I saw if you've ever been to my office, which most of you have not, Veronica has, there's a bunch of sticky notes on the monitor. One of them says that there's a paper on ePrint that uses a non-transitive group action for some kind of secret sharing thing. So codes might be a good candidate for that. We often need rigid codes. A rigid code is a code with a trivial homomorphism group. Do we have a mechanism to construct rigid codes or even prove that codes are rigid? This is not a very well understood problem as far as I know. Group actions are big now. What other group actions can we use for this stuff? There's a bunch. If you look at the NIST competition, there's a new signature competition. There's like a bunch of signatures based on group actions. Okay, so quickly acknowledging funding from CCI, Southwest Virginia, Virginia Tech, and Kinika Patatuchiki, the Ministry of Business Innovation and Employment. Thanks, everyone.
Very much. Jason, any questions from the audience too, from the online audience? You can write your question or unmute yourself.
Oh, thank you. We're discussing in the chat.
No question, more answers.
That's fine. That's fine.
Okay. Thank you, Jason.
Yeah, thanks for having me.
Okay.